Good morning, class. Today's lecture is going to focus on synchronous counters. We have already dealt with asynchronous counters, and today I'm going to show you how to design a synchronous counter. By synchronous counter or by synchronous, what we mean is that all the flip-flops are connected to a common clock. And by so doing, all the outputs will change at the same time. In designing a synchronous counter, there are some few procedures that we will go through before finally you can design your counter. The first one in designing a synchronous counter is what we call, you first draw the state diagram. You draw the state diagram. You ask, what is a state diagram? A state diagram describes different states in a sequential circuit. And in a state diagram, a state is represented by a circle. So if I have this, which means I have 1, 2, 3 states. So a state is represented by a circle. Now, there is an arrow that transition from one state to another. So let's say I'm moving from state 0, 0, 0 to state 0, 0, 1. This arrow shows me that in the state diagram, there's a transition from 0, 0, 0 to 0, 0, 1. Likewise, there's going to be a transition from here to 0, 0, 2, and then from 0, 0, 2 to 0. So in a state diagram, that is the first thing in designing a synchronous counter you need to do. You draw a state diagram. The second thing you do in designing a synchronous counter is to determine the number of flip-flops and type of flip-flops. For example, if we want to design a 2-bit counter, we will need 2 flip-flops. Remember that a flip-flop can store only 1 bit. So if we want to design a 3-bit synchronous counter, we will need 3 flip-flops. And then the type of flip-flop. We have various types of flip-flops. So which of the types are you going to use in designing your counter? Is it a JK flip-flop, a T flip-flop, a D flip-flop, or what? So you have to determine the type of flip-flop that will be required or you need in designing the synchronous counter. After the 2, the next thing that you do again is to develop what you call a citation table. So you obtain an excitation table, that is point 3. And this excitation table is developed from a transition table. Okay, every flip-flop has its own transition or excitation table, as you know. So for a JK flip-flop, if you are going to use a JK flip-flop in your design, you need to have the excitation table for the JK flip-flop. If you want to use a T flip-flop, you need the excitation table for the T flip-flop. From the excitation table, you now develop the circuit excitation table. Circuit excitation table. Circuit excitation table. And what is it? This is your design. So if, for instance, I'm going to design a 3-bit counter, I've drawn my state diagram, I've determined the number of flip-flops that I'll need. Now I need to obtain the circuit excitation table for my design. Okay, and you get this from the excitation table of a particular flip-flop that you are going to use. Okay. Now the fourth thing you do is to minimize your design, and you do that by a kind of map. Draw a key map. After going through all the four, then finally you draw or you design the circuit. Okay, so these are the 5 steps that you go through while you design a synchronous counter. You develop the state diagram, or you draw the state diagram. You determine the number of flip-flops you are going to use and the type of flip-flop. Remember, in examination, I will tell you the type of flip-flop to use so that everything will be uniform. Okay, but on your own, when you want to design any synchronous counter, what you do is that you determine the type of flip-flop and then the number of flip-flop that you use. The third is to draw the excitation table for the particular flip-flop, and out of that excitation table you obtain the circuit excitation table for your design. From the circuit excitation table, you map everything on a key map. Okay, and then finally you do your design. So these are the 5 steps that you go through in designing a synchronous counter. Now let's take an example. Okay, we want to look at an example by going through these steps. And in this example, we are going to design a 2-bit up synchronous counter. Okay, we are going to design a 2-bit synchronous counter, but we want to count up. As I've told you, we can either count up or we count down. Either I count 0, 1, 2, 3, 4. In that way, I'm counting up. If I count from 0, then 3, 2, 1, then back to 0, that's a down count. So in this simple design, we want to look at a 2-bit synchronous counter. As I told you, the first thing to do is to draw the state diagram, and it's a 2-bit. Okay, so we draw the state diagram of a 2-bit. Note that in 2-bit we have 0, 0, 0, 1, 1, 0, and then 1, 1. That is why we have 4 states. Okay, so we have 4 states in designing the 2-bit synchronous counter. So we have 0 0 0 1 1 0 and then 1 1. Then how is the transition going to look like? So from 0 0, the count should go to what? 0 1. From 0 1, we count 1 0. From 1 0, we count 1 1. And then from 1 1, we go back to 0. Okay, so this is the first thing we do. That is the state diagram. So this is the state diagram for our 2-bit synchronous counter. Okay, now what type of flip-flop do you want to use? In this design, I'm going to use JK flip-flop. Okay, and because it's a 2-bit synchronous counter, the number of flip-flop that I'll need is got what? 2. So I'll need 2 flip-flops in this design. Okay, so that is the second on our list. Then the third one, what do we do? The third one, we come out with the excitation table. And because I'm choosing a JK flip-flop, I have to draw the excitation table of a JK flip-flop, okay, of which you know already. So this is the excitation table of a JK flip-flop. Let's do it together. Okay, so let me see, let me divide into 2. This is too much, no problem. So in the excitation table, you know we have the present state and then the next present state. Okay, and then we are going to get our J and then the K, which will be the inputs. Okay, so this side is the output transition. So we have our output transition here, and then we have our flip-flop input here. Okay, so we know if the present state is 0 and the next present state is 0, for a JK flip-flop, we know the J will be 0 and the K will be don't care. This we have done in class, so you don't have a problem. Okay, if the present state is 0 and then the next present state is also 1, for a JK flip-flop, J is equal to 1 and K is what? Don't care. If the present state is 1 and the next present state is 0, for a JK flip-flop, then what it means that the J is what? Don't care, and then the K is 1 because we are resetting it. Okay, and if the present state is 1 and the next present state is also 1, then it will toggle. So here will be 0. No, don't care, and then 0, don't care, and then 0. So this is our excitation table for a JK flip-flop, and we are going to use this excitation table to draw or to develop our circuit excitation table. So let's do our circuit excitation table. Now, so these are still diagram 0 0 1 blah blah to 0 0. Okay, we are going to use 2 flip-flop. So this is the MSB, this is the LSB, right? Okay, so I'm going to develop the excitation table or the circuit excitation table. Let's do it together. Okay, so let me split it into two like this, and then here. Okay, so over here, so I have my input here, which is the JK input, and then I have my, let me split it into 2. I have my present state and then the next present state, right? Okay, I have it here. So in the present state, I'm going to have two columns. Okay, and here too I have two columns. Two columns here. Okay, so I'm going to have B here and then A here, or let me say QB and then QA, because Q, so this is the present state, so this QB plus and then this is QA plus. Okay, the arrangement can change, but be careful when you are drawing. Okay, so if, let me use black pen, or red will do. Okay, so if the present state is 0, let's say I have 0 0, then 0 1 1 0 1 1. Okay, so this will be the present state. Now, so let's look at it from the state diagram. From 0 0, the next state is what? 0 1. So here will be what? 0 1. So this is the next state, 0 1. From 0 0, it moves to 0 1. From 0 1, it moves to 1 0. So 1 0. From 1 0, it moves to what? 1 1. From 1 0, it moves to what? 1 1. And then from 1 1, it gets what? 0 0. Okay, I believe you got it. So this is the present state. So when the present state is 0 0, from 0 0, the transition is to 0 1. So 0 1. From 0 1, which is the present state, current present state, the transition is what? 1 0. And then from 1 0, 1 1, 1 1, you get to 1 0. Right. So I believe you are okay with that. Now, so here I have B and A. So I'm going to get JB and then KB and then JA and then KA for my input. Okay, I'm using a JK flip-flop, and you know that JK flip-flop has two inputs, the J and then the K. Okay, very good. This is what we do. Now, when the present state is 0 and then the next present state is 0, now you compare this to your excitation table. When the present state is 0 and then the next present state is 0, for a J grid, for J is equal to 0 and the K is what? Don't care. Now, when the present state is 0 and the next present state is 1, we are comparing the present state of QB to the next present state of what? QB. That's what we are doing. So when the present state is 0 and then the next present state is 1, now you come to the excitation table. When the present state is 0 and then the next present state is 1, the J is 1 and then the K is don't care. So 1 don't care. Okay, now we do same. When the present state is 1 and the next present state is 1, here it is don't care, then 0. And then finally, when the present state is 1 and the next present state is 0, so present state is 1, the next present state is 0, it is don't care 1. So I'm done with the B. Okay, so I'm going to do for the A. So you look at the A column against the next present state using the A column. So I'm going to match these two, this and that. Okay, now when the present state is 0 and then the next present state is 1, from the transition excitation cable, 0 and 1 is what? 1 don't care. So 1 don't care. When it is 1 and then the next state is 0, 1, the next is 0, is don't care 1. So don't care 1. When it is 0 and then it is 1 here, 0, 1, it is 1, don't care, 1, don't care. And then finally, when it is 1 and the next state is 0, 1, 0 is what? Don't care 1. Okay, so we have been able to develop, so this is what I call your circuit excitation table. Your circuit excitation table. Okay, so this is the circuit excitation table we refer to in the procedure of designing the synchronous counter. So after doing this, the next thing to do is to map the excitation table on a Karnaugh map. So we have 1, 2, 3, 4. So we need 4 Karnaugh map. And because it is J and K, it's going to be a 2 input Karnaugh map. Okay. So we are going to look at the present state against the input. So Karnaugh map. So we draw the Karnaugh map. So 2 input, okay. So let's see, this is B and then this is A. Okay, so this is 0, 1, 0, 1. I'm going to do 4 of them. Zero, 1, 0, 1. Okay, so these are 4 K maps. Now we are going to map. Okay, I'm going to do for JB. Oh, sorry. So here should have been QB. So here will be QA and then QB because we are dealing with the Q's. So here will be Q and then Q. Okay. Now, when QB is 0 and QA is 0, that is 0, 0, J is equal to what? 0. So this is 0. When QB is 0 and then QA is 1, so 0, 1, this is what? Don't care, right? No, it's 1. We are doing this. It's 1. 1, 0 is 0. And then 1, 1. 1, 1 is what? Is 1. Okay. So we minimize the expression. We minimize the expression. And then when we do that, we have JB is equal to what? A. Because the B will cancel and the A is common. So we've gotten our JB. Oh no, sorry, it's going to be QA. QA. It's going to be QA. This is QA. Okay. So let's do the same for the K. So we are going to do for the K in this column, K. Okay. So 0, 0 is what? Don't care. 0, 0 is what? Don't care. Okay. And then 0, 1. So 0, 1 is also what? Don't care. Okay. And then 1, 0. 1, 0 is 0. And then 1, 1 is 1. Okay. So we can, so it means KB is also equal to what? QA. Right. Now let's do for the next column, that is JA. JA. So we have 0, 0, 0 0 is equal to what? Is equal to 1. Okay, then we have 0 1 is equal to don't care. So 0 1 is equal to what? Don't care. Okay, and then we have 1 0 is equal to 1. 1 0 is equal to 1, and then finally 1 1 is equal to don't care. Don't care. So with this one, we can see that we can group all this, and then we can see J A, right? Yes, J A is equal to what? 1. So this J A is equal to 1. One more to go. One more to go. So let's go. So here 0 0 we are doing for the key column. So 0 0 is what? Don't care, right? 0 0 is don't care. 0 1 is what? 1. 1 0 is don't care. 1 0 is don't care, and finally 1 1 is 1. Okay, so we can group it. It's 4. Can group it, right? So that's our grouping, and we can say that our KA is also equal to what? 1. Okay, so as a summary, this is what we have. We have JB equal to QA. We have KB is equal to what? QA. We have JA is equal to 1, and then we have KA equal to 1. So now we can draw our circuit. We can now draw our circuit. That is the final part of the design procedures. So we are doing a JK flip-flop. So 2-bit counter. So I have this is a 2-bit counter. So this is my yes, B is my MSB. So this is my JA, this is my KA, this is my JB, this is my KB. Okay, this is going to be my QA, and then this is going to be my QB. Okay, now so I have my J. Okay, now it's a synchronous counter, so I need my clock, positive triggered. So I need my clock, which is here. Okay, yeah, okay, so let's continue the design. Now JB is equal to QA. This is JB, it's QA. So this QA comes directly connected to this. KB is equal to QA. So this KB. So it means from here I can tap it. Okay. JA is equal to 1. So K is equal to 1. So I'll tie J and KA to 1 or high. Okay, so this is flip-flop A, and this is what? Flip-flop B. So this is QB, and then here is what? QA. So that is my circuit diagram for 2-bit synchronous counter. Okay, so that is it, and we have designed it. Okay, so let's go over again. So we are to design a 2-bit up synchronous counter. First, we come out with the state diagram. from the state diagram, we determine the number of flip-flop. We said we are going to use JK flip-flop, and the number of flip-flop is what? 2. So you can see we have 2 flip-flops. 1, 2. Then we came up with our excitation table for the JK flip-flop, which you know already. So from the excitation table, we developed the circuit excitation table. Okay, then we map everything on a Canvas map. We minimize the expression, and then we draw the circuit. I hope you understood. Take your time, go through, and in the next lecture we'll take another example.